Okay, I want you to picture something for a second. It's going to sound a little like a physics problem from hell, but just bear with me.
All right, I'm listening.
Imagine you've been shrunk down. You are now the size of an ant.
Okay, I'm an ant. What am I doing?
You're holding a laser. And not just some little laser pointer. This is a laser powerful enough to vaporize metal.
Got it. Ant with the death ray.
In front of you, a machine shoots out this tiny, tiny droplet of molten tin. It's maybe the size of a white blood cell. And it's flying past you at 250 kilometers per hour.
That's incredibly fast.
It gets worse. Your job as the ant is to shoot that droplet with your laser. But you don't just hit it once, you have to hit it twice. Twice. And you have to do all of that within a window of about 20 microseconds.
I'm going to go out on a limb and say that sounds, well, physically impossible.
It should be. But here's the real kicker. You have to do this 50,000 times. Every single second.
Okay.
And if you miss, even once, the entire global supply chain for advanced computing just grinds to a halt.
And what you're describing, it sounds like complete science fiction, but it's actually the daily operation of ASML's Extreme Ultraviolet lithography machine, the EUV machine.
It's arguably the most complex commercial product humanity has ever built.
Without a doubt. And the stakes are just immense. We're talking about a machine that costs somewhere between $350 and $400 million.
For a single machine.
For one. And almost every advanced microchip in your phone, your laptop, the AI servers everyone's talking about, they only exist because this machine pulls off that impossible trick.
So today, in this deep dive, we're going to explore how one company managed to, well, basically beat the laws of physics to save Moore's Law.
And this isn't just a story about clever engineering. It's really a story about unreasonable people who overcame 30 years of doubt and skepticism.
So let's get into it. To really understand why anyone would build a machine this insane, we have to go back to the wall the tech industry hit, what, around 2015?
Right. We all know Moore's Law, the idea that computing power doubles every 2 years.
But it's really about the density of transistors, isn't it?
Exactly. For 50 years, we just kept making them smaller. Smaller transistors, faster chips, less power. But eventually, the industry just hit a brick wall.
And it wasn't just a physics problem, it was an economic one, too.
That's the key. The cost per transistor stopped dropping. That was the crisis. But the root cause was absolutely physics. Chip making, photolithography, it's basically like shining light through a pattern.
Like a stencil.
A stencil, or a mask is the technical term, onto a silicon wafer. It's like using spray paint.
Simple enough, until the holes in your stencil get smaller than the droplets of your spray paint.
That is a perfect analogy. The industry was using deep UV light, which has a wavelength of 193 nanometers, but they wanted to print features much, much smaller than that.
And that's where the villain of our story comes in. The Rayleigh equation.
The Rayleigh equation,
Yeah.
Yes. This is the formula that dictates how small you can possibly print. The formula itself is CD equals K1 times lambda over NA.
Okay, let's translate that into English for everyone.
Right. So CD is the critical dimension. That's the smallest line you can print. To make that number smaller, you really only have two knobs you can turn.
Okay.
You can make your lens bigger, that's the NA, or numerical aperture, or, and this is the big one, you can shrink the wavelength of the light you're using, the lambda.
And they'd already pushed the lens size, the NA, as far as it could go at the time.
They were maxed out, so they had to change the light. They had to make a huge leap from a wavelength of 193 nanometers all the way down to 13.5 nanometers.
Extreme Ultraviolet.
Yeah.
EUV.
Exactly.
But if they knew they needed 13.5 nanometer light, why did it take 30 years? I mean, why not just build a light bulb that emits that color?
Because that light doesn't really exist naturally on Earth. It's basically a soft X-ray. The problem is it's absorbed by almost everything.
Everything. Like what?
Air absorbs it, glass absorbs it. If you tried to shoot an EUV beam across this room, it wouldn't even make it an inch.
So step one, right away, the entire machine has to be a vacuum.
A massive, massive vacuum chamber. But step two is much harder. You have to generate the light. And the only natural source of this kind of light is, well, the sun.
So they literally had to build a star in a jar.
A star in a box inside a factory. And this brings us right back to our ant and that little tin droplet. This is challenge number one, the source. They settled on a method called laser-produced plasma.
Which is really just a polite engineering term for blowing things up.
Pretty much, yeah. They use a generator to shoot those molten tin droplets we talked about. Now, keep in mind, these things are coming out of a nozzle that's vibrating chaotically.
But the droplets have to be perfect.
Perfectly spaced and identical. And then comes the double tap. This was the real breakthrough that saved the project.
Because just hitting it once wasn't working.
No, it wasn't powerful enough, not efficient enough. If you just hit a sphere of tin with a big laser, you don't get enough plasma. So they developed a two-pulse system.
Okay.
Pulse 1 is a pre-pulse. It's a lower energy laser that just hits the droplet and flattens it.
Like a pancake.
Exactly, a little tin pancake. That increases the surface area. Then, just microseconds later, the main pulse. A huge carbon dioxide laser hits that pancake and just vaporizes it.
And when you say vaporize?
I mean, it creates a plasma that reaches 220,000 Kelvin.
Which is what compared to the sun?
That's roughly 40 times hotter than the surface of the sun. And that specific plasma at that specific temperature is what finally emits the 13.5 nanometer light they need.
And this happens 50,000 times a second.
Actually, the newer sources are pushing towards 60,000. The timing, the synchronization, it's just mind-boggling. The engineers have an analogy for it.
I want to hear this.
It's like hitting a golf ball into a hole from 200 meters away while the ball is traveling through a tornado.
Wait, hold on. A tornado? You just said the whole machine has to be a vacuum because air absorbs the light. How can there be a tornado in a vacuum?
That is the incredibly clever and slightly terrifying part. The chamber isn't a perfect vacuum. It's actually filled with hydrogen gas flowing at hurricane speeds, but we'll get to why in a minute.
Okay, let's put a pin in the hydrogen hurricane. Let's talk optics. You've made your artificial sun, you have the EUV light, now you have to focus it to print the chip. Normally, you'd use a lens.
But you can't. You said it yourself. Glass absorbs EUV. If you put a glass lens in front of an EUV beam, it just goes dark. So the entire optical system has to be mirrors.
And I'm guessing not the mirror for my bathroom.
No. These are, and this is not an exaggeration, the smoothest objects ever made by humans. They're built by Zeiss in Germany. To give you a sense of the scale, if you blew one of these mirrors up to the size of the entire country of Germany.
A Germany-sized mirror. Okay.
The biggest bump on that entire surface would be less than 1 millimeter high.
That's hard to believe. How do you even measure a bump that small on a surface that massive?
With interferometers and lasers that are just as precise as the ones creating the light. Here's another way to think about it. If you scaled the mirror up to the size of the Earth, the biggest imperfection would be no thicker than a playing card.
Unbelievable.
They have to be that flat. Any little imperfection scatters that tiny wavelength of light and completely ruins the image you're trying to print.
But there's a paradox here. Even if the mirror is perfectly smooth, materials still want to absorb EUV light. So how do you make a mirror reflect something that doesn't want to be reflected?
You use something called a Bragg reflector. It's a multi-layer sandwich. They lay down alternating layers of silicon and molybdenum, maybe 40 or 50 pairs of these layers.
And that's what reflects the light.
Each layer interface reflects just a tiny bit, and they're spaced perfectly so that all those tiny reflections add up through constructive interference.
But it's not 100% reflection, is it?
Oh, not even close. The best they can do is about 70% reflectivity.
Which sounds pretty good until you start doing the math on all the bounces.
Exactly. The light bounces off 6 mirrors in the projection system, plus the mask, plus the mirrors in the illuminator. So you lose 30%, then another 30% of what's left, then another.
By the time the light actually hits the wafer?
You're left with only about 4 to 8% of the light you started with.
Which explains why the source has to be so ridiculously violent. You start with this miniature sun, just to get a tiny trickle of usable light at the end.
Precisely, and that creates a whole new problem. Where does the other 96% of that energy go?
It gets absorbed by the mirrors as heat.
As heat. And heat makes things expand.
And if your mirror expands by even a single nanometer, your focus is gone.
Gone. So Zeiss had to build this incredible nervous system of sensors and actuators right into the back of the mirrors to constantly warp them back into the perfect shape to compensate for the heat.
The pointing accuracy on this is just ludicrous. I read it's like shining a laser from Earth to the moon.
And being able to choose which side of a dime to hit.
It's just manufacturing at the absolute end of physics.
Okay.
Okay, so let's get back to that tornado you mentioned. You have these impossibly delicate, perfect mirrors. And right next to them, you're exploding tin droplets 50,000 times a second.
Right. This is what they call the debris nightmare. You've got plasma, you've got ions, you've got vaporized tin flying everywhere. If a single nanometer of that tin lands on one of those Zeiss mirrors, The reflectivity drops, and your $350 million machine is ruined.
So this is where the hydrogen hurricane comes in.
This is it. They flush the entire chamber with hydrogen gas moving at 360 kilometers per hour. That's a Category 5 hurricane.
Why hydrogen, though? Why not something like nitrogen or helium?
Two big reasons. First, hydrogen is the lightest element, so it absorbs the absolute least amount of EUV light. It's the only gas that's transparent enough. But second, and this is the key chemical insight, hydrogen reacts with tin.
It cleans it off.
It reacts to form a gas called stannane. So instead of solid tin plating your mirrors, it turns into a gas that you can just vacuum out of the system.
So it's a self-cleaning oven, but the cleaning agent is a hurricane, and the oven is constantly exploding.
A hurricane that has to survive a supernova. Because you have to remember, those plasma explosions create these massive shock waves. Scientists figured out that the physics describing these tiny explosions are the same physics used to describe actual supernovae in space.
You're kidding.
It's called the Taylor-von Neumann-Sedov formula. So you have these miniature supernova blast waves going off 50,000 times a second, interacting with a hydrogen hurricane inside a vacuum. It sounds like something that should not work.
And for a long time, it didn't.
It didn't. The collector mirrors, the first ones to see the light, kept degrading, and they actually found the solution by accident. An engineer noticed the mirrors stayed cleaner when the machine was opened up to the air for maintenance.
That feels completely counterintuitive. You'd think air would bring in dust and contaminants.
You would. But they figured out that a tiny, tiny amount of oxygen reacting with the UV light was helping to scrub carbon buildup off the mirror surfaces. So they started intentionally injecting a microscopic amount of oxygen into the vacuum.
An accidental fix.
A totally accidental discovery that basically made the machine commercially viable.
Hearing all of this, the blast waves, the mirrors, the gas flows, it makes total sense why the industry was so skeptical for so long. This wasn't a quick project.
Oh, no. We're talking decades of doubt. It really started back in the 1980s. A Japanese scientist, Hiro Kinoshita, and an American researcher, Andy Hawryluk, and honestly, they were ridiculed.
I think they called it the big fish story.
That's exactly what industry experts called it. Andy Hawryluk tells these stories about being literally laughed off stage at conferences. The engineering challenges just seemed insurmountable.
And the big American companies, Intel, AMD, Motorola, they tried to build this themselves at first, right?
They did. They formed a consortium, EUV LLC, but one by one, they all gave up on building the machine. It was just too hard, too expensive. They figured they could just buy one later if some other company was crazy enough to actually make it work.
Which left ASML, this little spin-off of Philips in the Netherlands. They were the only ones unreasonable enough to keep going.
They were, but they didn't have the cash to finish it on their own.
No, and this is such a crucial part of the story. Around 2012, ASML was hitting the valley of death. The R&D costs were just spiraling, so they went to their biggest customers, Intel, Samsung, and TSMC.
And they basically said, look, if you want this machine to exist, you need to help pay for it now.
The great pre-competitive collaboration.
Exactly. These companies are the fiercest of rivals. They can't stand each other. But they all realized that without ASML succeeding, none of them had a future. So Intel pumped in about $4.1 billion. Samsung and TSMC put in billions more.
They weren't investing for profit. They were investing for survival.
That's it. There was no plan B for Moore's Law. And ASML did something incredibly bold with that money. They decided to start developing the next generation machine, the High-NA system, before the current one even properly worked.
That's a real burn-the-boats strategy.
It was. The pressure was unbelievable. There's this funny anecdote about an ASML executive in Kinoshita visiting a chapel during a really rough patch. They lit some candles, praying for the source power to go up.
And did it work?
They claim there was a statistical correlation between the prayers and the laser power output increasing the very next week.
I'm not sure we can credit divine intervention for plasma physics, but hey, I'll take it. So let's fast forward to today. The machine works. It's shipping. But what's the practical reality of running these things?
It's a beast. We've talked about precision, but we haven't really talked about speed. To make back that $400 million price tag, one of these machines has to print around 185 wafers an hour.
Which means the mask, the stencil, has to move back and forth incredibly fast.
Incredibly fast. We're talking accelerations of over 20 Gs.
20 Gs? That's what, 5 times a Formula One car?
5 times a Formula One car. But here's the crazy part. If you accelerate something that fast, it wants to vibrate. It wants to shake.
But it can't.
It can't. It has to stop and start and overlay the next layer of the chip with an accuracy of less than 1 nanometer.
An error margin of about 5 silicon atoms.
While moving faster than a fighter jet in a dogfight. It's just absurd. And even just shipping one is a logistical nightmare. It takes 250 shipping containers and fills 7 Boeing 747s.
And you mentioned high NA earlier. That gamble they took, that's the new version that's shipping now, right?
Yes, high numerical aperture. Remember our Rayleigh equation, we've hit the limit on the wavelength, the lambda. So the only knob left to turn to print smaller features is the lens, the NA.
You have to make the lens bigger.
But if you make the lens bigger, the angles of light get too steep and the mask starts to cast a shadow on itself. It's a geometry problem.
So how did they solve that?
They used a trick from old Hollywood movies. Anamorphic optics.
Like CinemaScope?
Exactly like CinemaScope. They squeeze the image. They shrink it 4x in one direction and 8x in the other. It allows them to use a bigger, more powerful lens without making the mask itself impossibly large. It's the next step to keep Moore's law alive.
So we have a machine that's using supernovas, hydrogen hurricanes, and cinema lenses to print the brains of our digital world. But beyond the sheer wow factor, what's the real takeaway here?
For me, it comes back to the nature of progress, the consensus trap. If you look back at the history of EUV, the reasonable view was always that it was impossible.
It was reasonable to say you can't hit a tiny droplet with a laser twice at that speed.
It was reasonable to say you can't make a mirror that smooth. It was reasonable to say the debris would destroy the optics. The people who said it's impossible were the rational ones.
But they were wrong.
They were wrong because a small group of people, Kinoshita, Harry Luck, the team at ASML, the executives who wrote those massive checks, they just refused to be reasonable. There's that great quote adapted from George Bernard Shaw.
Which one is that?
The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. Therefore, all progress depends on the unreasonable man.
That's the perfect summary. We owe our entire digital lives to a handful of unreasonable people.
We really do. And, you know, it makes you wonder about the other impossible things out there today.
Like what comes to mind?
Well, think about fusion energy or true quantum computing. We look at them now and we see all the reasons they won't work. The engineering is too hard, the physics is too complex, the costs are astronomical.
But maybe they're just stuck in their own 30 years of skepticism phase.
Exactly. They could just be waiting for the right unreasonable person to come along and push them over the finish line.
A fascinating thought. That impossible is just an engineering problem waiting for enough money and, I guess, enough stubbornness. Thanks for listening to this deep dive.
My pleasure. Stay curious.
See you next time.